see the screen?
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
Yes, sir.
So yesterday, I am sorry for the entire problem. There was a power cut in our institute yesterday. Anyway, so we were here, the logarithmic function. So for a non-zero complex number, we defined log z yesterday this way. Log z is just log mod z plus I arg z. And as we know, this argument is not a single valued function. It is a multi-valued function. And how to get all the values of this function? This way. You choose, one of the half open interval in real line of length 2 pi, as I said yesterday and the day before. And then you can get a single valued argument, okay, when argument belongs to that interval. And accordingly, one can define, one can find all possible values of argument. So in particular, if we choose this interval, minus pi open and plus pi closed, so we have the principal argument, okay, and we obtain all values of arg z in this way. So therefore, we have all values of log z this way, log mod z. This is real logarithm. We all know about it. And this is the rest part is I times this guy, where k runs from k runs over all the integers. So if we restrict, if we want to make it a single valued function like what we did with arg z, okay, then we have to choose only one k. For example, if k is equal to 0, you just look at this equality. If k is equal to 0, then we have log mod z plus I arg z. Okay, so this is single value definitely because the principal argument is single valued. So it has a particular name. So when argument of z lies in between minus pi and pi in this way, then we have a single valued function log z, and we call it the principal logarithm. I told it yesterday. Okay, so the principal logarithm is denoted with a capital L, and it is defined this way. So we have all the values of log z, as if you just look at this line and this line together, then it is the principal logarithm plus I to k pi, right? Where k runs over all integers. So a quick example. Nevertheless, if you choose some other interval, once again I repeat, if you choose other interval like, if you choose, say, 0 to pi, okay, so one side has to be closed and the other side has to be open. So it does not matter. This side can be open and this side can be closed, as I said always. So if we choose this thing, and if you want your argument to belong in this interval, okay, then you have another single valued function argument, okay. If you give it a name, like here we have given it a name. If you give it a name and if you call it, say, arg z cap, okay, arg z hat, in this way, just a name, okay, when argument lies here, then you can define log z accordingly. And indeed, you will get all the values of log z in terms of this argument. Here we are getting all the values of log z in terms of the principal argument. And nevertheless, you can choose any half open interval of length 2 pi. You have a single valued function arg z on that interval, and you can get all the values of argument in terms of that argument by using this guy, okay. And consequently, you have all the values of log z. So it does not matter which argument you choose, which interval you choose. But this is the standard convention that we choose always minus pi pi with minus pi open and pi closed. Okay, so this is the standard convention that is followed in mathematics. So we will just go along with it. So let us see a quick example. So what are the values of log 1 plus I? For example, we have chosen this z to be in particular 1 plus I. So this corresponds to the point 1, 1 in the complex plane. Okay. So you just plot it in your formula, whatever you have. So this is precisely we have, right? Log mod 1 plus I times its principal argument plus 2k pi, as we all know. And this is square root of 2. The modulus of this complex number is square root of 2. We all know this. And the principal argument of this is precisely pi by 4, the angle that it makes with the positive real axis, right? In the first quadrant. So this is the principal argument. So it has to be pi by 4. Okay. So these are the all values of log 1 plus I. And the principal value is, needless to mention this guy. So we have a quick example. Now I am going to make a statement which perhaps we all know. The values of log z are precisely the complex numbers W such that e to the W is equal to z. So you just look at the statement. The statement tells us that what are the values of log z? The values of log z are precisely those complex numbers W such that this equation holds. How do you prove that? So precisely, meaning it's just an if and only if condition. Okay. So how do you prove that? So first you put such a value like what we have. So let first you assume W to be whatever we know, log mod z plus plus 2k pi. So first you assume this where this key runs over integers. Okay. And you just verify whether this equation is satisfied. And what is e to the W? E to the W is, the exponential, the rules of exponential, the properties of exponential, it's additive, right? So it's just log z plus I plus 2k pi, which is precisely e to the log mod z times e to the I arg z times e to the I 2k pi. So we know about this, right? The values are distributed this way. And what is that? What is this quantity? Can anybody tell me? This is real logarithm. So what is that quantity? So this is precisely mod z, right? We know from the real logarithm, this quantity. And what is this quantity? This is e to the I theta, where theta is the argument, and this quantity is 1. Okay, so this is precisely mod z e to the I arg z. And what is that? Mod z, that is the modulus. So this is of this form r e to the I theta, right? So this is precisely the complex number z. So if W is of this form, then this equation e to the W equal to z is satisfied. Now the statement tells us that these are the precise values. Okay. Now how to prove that these are the precise values? So let us see the converse. So let W be U plus IV such that e to the W equal to Z. Now we show that W actually has this form. W is one of them, log mod Z plus IR Z plus 2k pi. So this is very, this can be verified very easily. So what is the polar representation? We have U plus IV equal to Z, that is so what is e to the U? What is e to the U? You just look at here. What is e to the U? So if I just write it as R e to the IV equal to Z, okay, then this R is precisely e to the U, which is equal to mod Z. This is the polar representation of this complex number Z, right? Okay. And what can you say about U? This U is real number. This U is real number. So from our knowledge of real number system, what do we have? How does U look like then? Okay. This is the knowledge of real numbers, right? This holds in real number system. Okay. The exponential is the reverse operation of log in real number system. We are using that. Okay. We are using that to prove the same for the complex numbers. That is what we are doing here. Okay. And this V is okay. And what is your V? V is a value of RZ, definitely, because this is the polar representation. It has to be a value. So if V is one of the values of RZ, then how does V look like? Therefore, V is the principal argument of Z plus some 2m pi for some m integer. Okay. So therefore, you just see how does this W look like. W is equal to U plus IV, which is log mod Z, what we expected actually, plus for some integer m. So this shows that these are the precise values, log mod Z plus I times RZ plus 2k pi, where k runs over the integers. These are the precise values for which e to the W is equal to Z. So in other word, we can say that, so this is the reverse operation. The logarithm is the reverse operation of the exponential, even for the complex numbers. Okay, so we shall get back to this logarithm and the exponential function for a second round of discussion after a break. Okay, we are taking a break from this complex numbers, the basic functions of complex numbers, and we are moving to define limit and continuity. And I guess all of you are familiar with this, but sometimes there are few things that we don't notice. So rather, I'd like to define all these notions in general for metric spaces. Okay. So the first thing that you notice is we can talk about a sequence in a metric space, right? What is a sequence of real numbers? Can anybody tell me?
Sequence is a function from set natural number to real number.
No, I can't hear the voice. I can't hear the voice.
Sequence is a function from set of real number to set of natural number to set of real number.
Yes, that is true. So a real sequence is a real sequence is a map F from N to R. Exactly. But here, when we denote a sequence, we always take the range set of this, right? Because here we collect just the range, its functional values, F2, F3, and blah, blah, blah. This is what we call a sequence. Sometimes we call it Xn. X1 is F1, X2 is F2, okay, and so on. So we just look at the range set of F, but it is indeed a function from N to R. So similarly, one can define sequence in any metric space in a similar fashion, right? So let us have a metric space. So let M D be a metric space. Then a map F from the set of natural numbers to M is called a sequence. You all know this. So it's called a sequence in M. Okay. So we denote it as I said, the range set. Since you know about sequence of real numbers, when do you say, if Xn is a sequence of real numbers, okay, and if nothing is stated, R is equipped with the Euclidean topology, meaning the topology induced by the modulus, the usual modulus, okay? So when do you say that Xn converges to X? When do you say limit Xn is equal to X? If Xn is a sequence of real numbers. Can anybody tell me, please?
If for every epsilon there exists n naught belonging to n such that for all n bigger than or equal to n naught, distance between xn and x can be made less than epsilon.
So you are saying precisely this, right?
Yeah, for every epsilon.
Such that
for every n,
yeah,
you can write
xn
this.
minus x less than epsilon
For all n bigger than
greater than or equal to n naught. Yeah, fantastic. Yes. So what exactly does it say? Yes, absolutely. This is the definition of convergence of a sequence. Okay. So a sequence Xn is said to converge to X in real line if this thing is satisfied. What does it tell us? What does it tell us? It tells us that, so if this is your X on the real line, this is your real line, say, then a sequence Xn is said to converge to X if every neighborhood, every basic neighborhood of X, it contains almost the whole sequence except for finitely many terms, right? The sequence is almost there in every neighborhood of X except for first finitely many terms. Okay, so all but finitely many terms of the sequence lies in every neighborhood of X. So this is the definition of convergence of a sequence in real line. Now I am going to define the convergence of a sequence in a metric space in terms of this definition. Okay, please remember this definition. So I have seen that when I teach here in IIT Bombay, I have seen most of the students, they don't have a clear vision of convergence. But the analysis is all about convergence. There is no second concept. It's all about convergence. Just believe me. The thing is that then when do you say that a sequence of real numbers converges to 0? If the limit is 0, then how do you deal with it? You will just remove x and put 0 here. Nothing else. You just remove x here. So it will be just mod xn, right? It will be just mod xn less than epsilon. Okay. So the thing is that we define the convergence in a metric space with the help of convergence in real line. How? Let us see. So we just make 2 steps. So step 1, as I said, a real sequence xn of real numbers, okay, is said to converge to 0. Someone is not muted. Please mute yourself. If, as I said, as you said, for every epsilon positive, there exists a natural number such that so this is the definition, that a sequence in real line converges to 0. Now in step 2, a sequence say an in a metric space MD is said to converge A, okay, if the real sequence D of En comma A, this is a real sequence, right? This is a sequence of real numbers, right? Whenever you apply D, if you can remember the definition of a metric, this is always non-negative. Okay, it maps M cross M to the right half of the real line. So this is actually a sequence of non-negative real numbers. So if the real sequence DANA converges to 0, so, and we know what is meant by a real sequence being convergent to 0 by step 1. So this is, we deal with in mathematics, we mainly deal with metric spaces. If you do complex analysis, you are in the complex plane. If you are doing analysis on Rn, you are in the Euclidean space Rn. all are metric spaces. If you do any kind of Banach space theory or Hilbert space theory, they are all metric spaces. So everywhere, the definition of convergence is same because they are metric spaces. Okay, a sequence an is said to converge to A if d of an comma A, this is a sequence of non-negative real numbers that converges to 0. And in this case, we use this notation, limit an to be equal to A, or simply we use this notation also, n converges to A. So do you remember this definition? It is so simple. There is nothing. An converges to A. What does it mean in a metric space? You just take the real sequence d of an comma A that converges to 0. And you know what is the definition of convergence of a real sequence to 0? What is given in step 1. Okay. So please, I request all of you to remember this. Okay. And the next thing is, I am going to state a common fact that if in a metric space a sequence has a limit, the limit is unique. Okay, so I am not going to prove them. Do you know why? Do you know why? If a sequence has a limit.
So Hausdorff.
Yes, because every metric space is Hausdorff.
Yes.
Meaning, any 2 points which are distinct can be strongly separated by means of a pair of disjoint open sets. Okay. So if a sequence has a limit, then the limit is unique. So I'm going to tell you some more facts about sequences. For example, you all know the definition of Cauchy sequence. What is a Cauchy sequence in a metric space? So I am defining them for metric spaces because the space of complex numbers itself is a metric space. So it's more general. So a sequence xn in a metric space is said to be Cauchy when, who can tell me? If come on, you guys must know the definition of a Cauchy sequence, right?
D of xn xm. Sir?
Yes. D of xn xm
Converges to 0.
Yes, precisely. Because here you see, thank you very much. Because here you see how have we defined the convergence of a sequence? It's in terms of a real sequence, right? You just look above, you just look at the cursor. D of n comma a converges to 0. This is a real sequence. So we define the Cauchy sequence in an analogous manner. We just push forward everything to the real line. We know the notion of Cauchy sequence in a real line. A sequence in real line is said to be Cauchy if mod xn minus xn goes to 0 as mn goes to infinity. We know that, right? So we just push forward everything from a metric space to the real line. If d of xn comma xm, this so this gives the distance between xn and xm, right? This gives the distance between these two terms, xn and xm. So terms are coming close and closer as mn approaches infinity. Okay. So this is what is quasi-sequence, right? As you move towards infinity, the terms will get close and closer. This is the basic notion. And this is the distance between two terms, right? So this converges to, and this is a real sequence. This converges to 0 as both m and n goes to infinity. So you can write it in terms of your, the definition that you know. You can write it accordingly. How? That is, for every epsilon positive, you can find out natural number n such that this guy is less than epsilon for all mn. So this is the definition of quasi-sequence in a metric space. Okay. So quick lemma, and I shall request you guys to show me a proof. So a quick lemma. Every convergence sequence is a quasi-sequence in a metric space. This MD is a metric space, is a quasi-sequence. That means if a sequence converges, then the terms of the sequence will come close and closer as in m and n approaches infinity. Okay, as we move towards infinity. So can anybody give me a quick proof of this?
Yes, sir. So we can use triangle inequality.
Yes, exactly. Thank you.
Yes.
So yeah, she is absolutely correct. So what she is saying, I am just following what she is saying. Okay. So let you have xn be convergence sequence, and let xn converges to x. This is a standard notation as I have mentioned above. Okay. So then what is the definition we have written above? This real sequence, this converges to 0, right? So therefore, we just deal with our boring machinery for every epsilon positive. You can find out n naught such that we have this therefore, one can easily see that d of xn, xm, as C was suggesting, this is, we know by triangle inequality, this is xnx plus d of xxm. And as you see, you can take it epsilon by 2. So as you see, this is less than epsilon by 2 plus epsilon by 2 when both m and n greater than or equal to n naught. Okay. So therefore, we have this, what we wanted is less than epsilon for all m n greater than n naught, and this is cosine. Okay, so this converges to 0 as m n goes to 0, and consequently it is cosine. So every convergent sequence is a quasi sequence. Does the converse hold? Does the converse hold? Can you
Yes,
please
sir.
say that again?
Yes, sir. Yes, sir.
In every metric space, does the converse hold?
No, sir.
Someone is saying yes, and someone is saying no.
Sir,
No.
we can consider open 0, 1 and 1 by n sequence.
So I am talking about a metric space, okay?
Yes, sir.
So what is your aim here? You are
Open
saying your
0, 1.
aim is open 0, 1. And what is your
1
D
by
here?
n. 1 by n.
No, what is your D? You have to make it a metric space first.
Usual matrix, sir.
It's your usual metric.
So what is the topology on 0, 1? The subspace topology of the real line, right?
Yes, sir.
Yes. And D is the usual modulus. Okay. Then this MD is a metric space, definitely. Where this 1 upon n, as you were saying, definitely is a quasi sequence which does not have a limit.
Sir, I think it's better to write closed at 1 because we are taking 1 by n. Sir, open at 0 and closed at 1.
Same, right?
So right hand side will be closed. That means open 0, closed 1.
Sir, we are constructing sequence 1 by n. For n equal to 1, 1 should be from the space.
Oh. Yes. So you want to include the term, the first term. So yeah, great. Thank you. So it does not have a limit in M. Okay. So the converse does not hold. The converse does not hold. And what can you say about the metric space of complex numbers? What can you say about it? What can you say about this metric space C with its modulus? It's a metric space, right? Is a metric space. And what can you say about quasi sequences here? Does every quasi sequence converge here in C?
Yes.
Yes, sir.
How do you prove that?
There is a complete space, so the Gaussian sequence is going to converge.
Indeed, this is true. So this is a metric space, okay, where every Cauchy sequence converges. So we just hello, can you hear me? Can you all hear me? Hello.
Yes, sir. Yes,
Yes,
sir.
sir.
Yes, sir.
Thank you. So we just reach the conclusion. We reach the conclusion that in complex number system, a sequence is Cauchy if and only if it converges. Because if it converges, it is Cauchy always. We have seen that holds in any metric space. Okay, but the converse also holds when we are in the Euclidean setting. So a sequence in C is a Cauchy sequence if and only if it converges. So I'm not just writing it. Okay, so the metric spaces where this thing happens, they are called the complete metric spaces. Okay, so I'm just writing down the definition. The metric is called a complete metric, and the metric space is called a complete metric space. A metric space MD is called complete if every Cauchy sequence in MD converges. Okay, then D is called a complete metric. This D is called complete metric. Okay, now briefly I'm going to define what is a limit. Perhaps you guys know it. So let f be a function that is defined on a subset E of the complex plane to C. Okay. Then f is said to have limit L as how do we denote this? If, please tell me the definition. If, what does it mean? If you just look at this whole thing, okay, if you just look at this whole thing, there are three things, right? This Z goes to Z naught, here FZ, and on the right hand side you have L. So what does this entire thing mean? When Z comes close to Z naught, FZ comes close to L, as simple as that. Okay. and we are in the Euclidean setting where the metric is given by the modulus. So we know the meaning of z comes to z naught. Mod z minus z naught comes to 0. Mod fz minus L comes to 0. That means fz comes to L. Okay. And in case when we are defining limit, this point z naught, it does not does not need to belong to E naught. Does not need to belong to the domain of definition E. Okay. If tends to L as z tends to z naught and z is not equal to z naught. Okay. And in mathematical notation, we say that for every epsilon positive, you can find out a delta positive such that this is implied by right. Z has to belong to E. Okay. So what does this mean? So this is just, this is just one line. We all know this definition, but what does this mean? If you just look at the right hand side, the right hand side means that it's a punctured disk, right? Mod z minus z naught less than delta, it represents an open disk in the complex plane with center at z naught and radius delta. And whenever you say this is strictly greater than 0, that means z is not equal to z naught. Okay, so the origin is removed. So that means simply when z belongs to this disk or this ball with center at z naught and radius delta minus z naught, you are removing the center, intersection with E, because z belongs to E also. So this will imply if z belongs to, am I correct? Whenever z belongs to this deleted neighborhood of z naught, fz will belong to the epsilon neighborhood of L. And this neighborhood is given, this neighborhood is obtained, this epsilon is given, and this delta is obtained. So given a basic neighborhood of L, you can find out a basic neighborhood of z naught such that whenever z belongs to the punctured disk, this disk is punctured at the center. Okay, z naught is not there. Definitely, it should not go beyond E. Then fz belongs to the corresponding neighborhood of L. So this is what is limit. When z approaches z naught, okay, inside the domain, and z naught may be outside the domain, it does not matter. Fz will approach L. So this is the fundamental thing. So we shall remember this. We are going to define continuity next. But before going to the continuity, I am telling you one thing. Whenever you are in a metric space, then the limit of a function can be characterized by means of sequence. That is what is called sequential criteria. Okay. So what is that? So we'll all know about this. A function if defined from as limit L as Z goes to Z naught, if and only if. We know the sequential criteria. What does it say? If xn goes to L for any sequence xn, for any sequence in E with xn not equal to x naught, sorry, better to say, Zn. I'm missing up. Yeah, Zn. With such that Zn converges to Z naught. So for any sequence that converges to Z naught, okay, and we are just ignoring the point Z naught as per definition. So this is what is called the sequential criteria for a limit, okay. And if you want to prove this lemma, you follow the real analysis, the techniques that you have learned from real analysis. The same result holds for a real function defined on a subset of real line, right? The sequential criteria for limit, okay. So you follow the same pattern. So we have a few properties of, I'm just recollecting them. If has limit at a point Z naught, then if is bounded near Z naught, meaning if is bounded in a deleted neighborhood of Z naught, okay. Further, if limit fz equal to L1 and if you have two different functions, then you have this.
Sorry, this Z tends to Z naught.
So, thank you. As Z goes to Z naught, Z goes to Z naught, then we have this. This is L1 plus L2.
I think the limit should be finite.
Yeah, we are talking about finite here.
Okay.
Whenever I say limit here, it's always L. This L This L is a finite, said to have limit L. Better I write belongs to C. Okay. L is always finite. I'm talking about finite limits only. Yeah. So we all know about this. Their pointwise product will give you back the product of limits. And number 3, if this L2 is non-zero, then you have limit. So whenever you write fz by zz upon zz, then you have to be careful about the zeros of G. So this is L1 by L2 provided okay in a neighborhood of z0, or better to write near z0. Otherwise, you will have trouble to write fz by zz, right? So we all know these properties, and we have already defined continuity. But how to define continuity in terms of a sequence or a limit of sequence? Okay. So f from C to C is said to be continuous at some z0. We know the definition. If for every basic neighborhood P of fz0 there is a basic neighborhood U of z0 such that f of u is contained in V. We'll know this definition, right? So how does a basic neighborhood look like in the complex number system with the Euclidean topology? So this is, so you can choose V to be, say, epsilon, okay, and U to be, say, wall around Z0 with radius delta. So that means f of this ball is contained in so this V is given, U is obtained. So this epsilon is given and this delta is obtained. So this is what is continuity. We all know this. So in other way, you can just write Z belongs to this guy, sorry, this guy, implies if Z belongs to epsilon. So how do you denote this set? This is just a disk. This is just an open disk with center Z0 and radius delta. And we have seen earlier, we have a short notation for this, Z minus Z0 less than delta, right? This is the way, if you can remember the previous class. And what is the notation for this? Right? So in other words, for every epsilon positive, there exists delta positive, such that mod fz minus fz naught less than epsilon whenever so this is what we know. The last line that I have written, that is what we know. We use as the definition of continuity. And whatever we have defined in topology, that the inverse image of a basic open neighborhood or a basic open set containing fz naught, okay, is open here. So they are same, you see, they are same. So this is the purpose of showing this. So this is the definition that we have learned from topology, right? Corresponding to every neighborhood V of fz0, you can find out a basic neighborhood U of z0 such that this thing holds if U is contained in V. And if you just proceed, what is meant by that? A basic neighborhood U around z0, it looks like this. And a basic neighborhood around fz0, it looks like this. And this is given, V is given, so this epsilon is given, U is obtained, so this delta is obtained, such that this thing happens. And if this thing happens, okay, so what does this mean? Whenever Z belongs to this ball, if Z belongs to this ball, right? And we have, as I said, once again, we have a shorter notation to denote this. The points in this ball is denoted by this. An open disk like this is denoted precisely like this. And we know how to denote a closed disk. We put a less than equal to here, right? If we put a closer over here. Anyway, we know how to have this shorter notation. And this is the definition of continuity. Now, if you want to have it in terms of limit of the function, like what we have, if you just look at the definition of limit here, you just look at, if Z belongs to the deleted neighborhood, then fz belongs to this neighborhood. So now here, what we have, Z belongs to this neighborhood, implies fz belongs here. Then can't we say that if Z belongs to even the deleted neighborhood, so this is a subset, this is a superset. So this will definitely imply if Z belongs to, okay, right. And what is that? That means this is limit Z goes to Z0, if Z is equal to, here A is if Z0, right? So the continuity can be interpreted in terms of this limit. And we have a sequential criteria for limit. So we have a sequential criteria for continuity. So thus, if it is continuous at Z0, if and only if limit as it goes to Z0, which happens if and only if the sequential criteria, this happens if and only if Zn converges to if Z naught for every sequence converges to Z naught. Okay. Now, if you choose to have a particular subset, okay, when if is defined on a subset E of C, okay, we consider the subspace topology of E. We consider so that means, whenever there is a neighborhood on the left hand side, you put an intersection with E, like what we have done in case of limit, right? So I guess now the notion of limit and continuity, though you guys are familiar with this, but I think this is now clear, right? Along with sequential criteria and everything. If you have any doubt or anything, so I have just recollected all these things, okay? We know about this. Now I want to get back to logarithm once again. If you have any question, please tell me.
Sir, what is the geometrical significance of the sequential convergence?
What do you mean by geometrical significance? It's just, you are in the complex plane and you have somewhere Z naught, and you consider sequence Zn that goes to Z naught. So it can be anywhere. The sequence can be anywhere and converge to Z naught. So this is your Z naught. It can be anywhere, any sequence. For all possible sequences, you have if Zn converges to if Z naught. This is what is happening here, nothing else. Okay. So I want to get back to the logarithm. So we have defined logarithm, right? So if you just look at the definition, there is nothing suspicious. It's the definition is clear. Okay. So this is the definition. It's defined for all non-zero complex numbers, and it is defined this way. Okay. So this argument is held fixed. You can choose some other arguments. Here, this argument lies in between minus pi and pi. As I said, you can choose some other also. Now, I am going to ask you one question here. If I talk about this as a definite function, as I said, this arc z, okay. So this is a function, right, from c minus 0 to minus pi pi, okay. My question is whether this function is continuous. So we are in the complex plane, and this is a function that is well defined and single valued, no doubt about this. This is your y-axis and this is your x-axis. This is your origin. Now the question is, in its domain of definition, that is c minus 0, this punctured complex plane, is this function continuous? What do you guys think?
No.
Can you please tell me where it is not continuous?
At pi, it will at the angle pi. At at z is equal to minus iota or minus 2 iota, there will be a sequence which converges to minus iota or minus 2 iota, but the image of the function will not converge.
Yes, exactly. Thank you. Exactly. What he is saying is absolutely what I wanted. The thing is that, you see, if you take any point on the negative real axis, definitely it is not defined at 0. So we just forget about the point 0. But if you choose any point on the negative axis, okay, any point alpha on the negative axis, negative x-axis, then you just look at the definition. You just look at the definition. If you have a sequence of complex numbers, Zn, that converges here from the second quadrant, okay, to alpha. And if you have some other sequence, say Yn, that converges to alpha from the third quadrant, then what should be the limit? What should be the argument? If you just look at a point like this, these are points. If you look at a point like this here, what is the argument? What is the argument of this point? You just look at, in the third and fourth quadrant, we measure the angle in the clockwise direction, in the negative direction, because it is minus pi to pi. And we measure the angles in the first two quadrants in the positive direction, right? In the anti-clockwise direction. So here the argument is between 0 and pi. If you just look at the first two quadrants, okay, so this is your minus pi, this is your 0, and this is your pi. So this is included and this is excluded. My point is that if you take a sequence from the second quadrant, a sequence of points Zn, then each Zn has its argument in this half, 0 to pi, right? Whereas if you choose a sequence from the third quadrant, its argument lies here. Okay. So can we have a limit then? I guess no. I guess no. Because the argument tends where? If Zn is a sequence in I'll just write Q2. This is quadrant, okay? And if Zn converges to alpha, okay? What is the argument of alpha? What is the argument of alpha? Can you please tell me what is the argument of any point lying on the negative half? You just look at the definition. What it should be? Minus pi or pi? Pi. It is pi. It is not minus pi. Minus pi is excluded. This is the reason minus pi is excluded. Okay, you can measure all points in the third and fourth quadrant in terms of 0 to in terms of minus pi to 0, except at minus pi, because you cannot say that its argument is minus pi and pi. So you have to take only one. This is the reason we choose a half interval, not a closed interval, right? A half open interval. Yeah, thank you very much. So then this converges to pi, okay? And what happens if Yn is a sequence in Q3, and if Yn converges to alpha, then it's clear that argument of Yn, it must converge to minus pi. Okay, so we can see that if you choose any point on the negative half of real line, then the function argument, though it is a well-defined function on the entire complex plane minus 0, it is not continuous on this line. But any point other than on this line, if you just remove this line, any point in the rest part, it is naturally continuous. There is no issue at all. So the principal argument is not continuous on the negative axis. What is the negative axis? Okay. I am excluding 0 because it is not defined at 0. So no point including 0. Okay. So if you want to make argument continuous, if you want to make this function, this principal argument continuous, okay. So what is the maximal possible domain on which it can be defined? Can you please tell me? Therefore, argument z from, what is the maximal possible domain on the left hand side? If you want to make it continuous, you have to remove this line, right? You have to remove this half line. Yes. Am I correct? C minus, yes. You have to remove this line, this half line, better to say. And here you have to include 0 because argument itself is not defined at 0. So we include 0 here. We remove 0 also. Okay. Is continuous. And this is the maximal possible, this is the maximal possible domain. This is the maximal domain on which this function is continuous. No doubt about this, right? So this ray, this closed ray should be removed from the complex plane if you want continuity of this function. Otherwise, just a function, it does not make any sense, right? Unless you have some beautiful properties of this function. Okay, I am not going to introduce differentiability or analyticity here. The next speaker will introduce all of them. So then you will find it more interesting even. So here what we are seeing is that we have a function, what is called the principal argument, that is defined on the entire complex plane other than 0, other than the point 0. Yet it is not continuous on C minus 0. If you want to make it continuous, then the best possibility is you just remove this half line. You just remove this half line. Okay? You just remove this half line from the plane and make this function look nice. Okay? Now I am going to define what is called a branch of logarithm. So let G be a region. Once again, I repeat, logarithm is one of the non-trivial concepts in complex analysis. One needs to learn it properly and clearly. So what is a region? An open and connected subset of C. Okay, it is open and it is connected. Continuous function f from G to C. See, I have chosen a continuous function, not just an ordinary function, is called branch of the logarithm if e to the fz is equal to z for all z belongs to G. You just look at the definition. This is called a branch of the logarithm in G. In G. Okay, I just wipe it and write it down. If you have this, so this is the definition. You have a region, you have a continuous function defined on that region, and this is called a branch of the logarithm if this equation is satisfied. E to the fz is equal to z. This is a composition of two functions, right? E to the z and fz both. Okay, so you just remember this definition. This is what is called a branch of the logarithm. This is a well-defined function. It is a continuous function. Okay, it is not a multi-valued function. It is a defined single-valued continuous function, and it is called a branch of the logarithm if we have this. Okay, so now the first question is, what can you say about this domain G? It is a domain or region in the complex plane, right? So what can you say about this region G?
Zero must not be there. Zero must not be there.
Exactly. That is what I wanted. Exactly. So the first thing is 0 does not belong to G. Why? Because we have e to the z exponential is non-zero for all z. Okay. Here you see e to the something is equal to z. So if e to the something is equal to 0, then we have a problem. Exponential function and its range does not contain 0. So 0 does not belong to G. That is the first and foremost condition that we want to have. Okay. Now, what can you say about the principal logarithm that we have defined? What is the principal logarithm? What is the principal logarithm?
Log mod z plus I into principal argument of z.
Yes. So this is plus I times the principal argument. Okay, and this is defined for all non-zero complex numbers. You know that. But the point is that, can we call it a branch of the logarithm? It is a well-defined function, but it is not continuous. If we want to declare this, we know that if we call this fz, if we take this to be fz on this domain, and if we call this G, if fz is this guy on G is c minus 0, okay, then what do we see? E to the fz we have seen this, right? We have seen as a remark. So this is equal to z, right? So this is what we have done in the beginning of today's class, right? Here, look at. So e to the this guy is equal to z. Okay, so in particular, if we choose the argument only k equal to 0, then it is z actually. Okay, so we have this equality here. So we don't have any problem with the equality. It is fine. Okay, but the point is that this function is not continuous. And if you just look at the definition, f has to be a continuous function on the given region. This is definitely a region, this G, but this is not continuous. This log Z is not continuous. Why? Because this argument is not continuous function. So if you want to make this principal logarithm a branch of logarithm, the way we have defined branch, what we have to do? We have to remove that closed ray from the complex plane. If we remove that closed ray, the negative x-axis from the complex plane, then this argument is a continuous function, and this guy is already a continuous function, no doubt about this. Then everything will be fine. This is a continuous function, this f then, okay, and this equation is satisfied, so it will be a branch of logarithm. So I just write, but this is not continuous on c minus 0. Okay, but if we choose G to be C minus this half line, then okay is continuous. On G, and also we have e to the fz is equal to z for all z in G. Therefore, the principal logarithm on this set is a branch of the logarithm. So we have at least one example of a branch of logarithm. Okay. So once again, please look at the definition, how we have defined a branch of the logarithm. We have to choose a region first, an open connected subset of C. We have to choose a continuous function f from G to C. Okay, and it has to satisfy this functional equation e to the fz equal to z for all z in this domain, in this region. Then we say that it is a branch of the logarithm. Now, just for example, what we have seen, if we choose the principal logarithm, it's a well-defined function, okay, and it is defined for all non-zero complex numbers, yet it is not continuous on c minus 0, because this function, this part, argument z, the principal argument, is not continuous on the negative real axis, though it satisfies this equation for all z. This equation is satisfied for all z in c minus 0 in this punctured plane. But it is not. But it is not a branch of the logarithm on c minus 0 because of the lack of continuity. Okay. Now we all know that the principal argument is continuous if we remove this half line, okay, the negative x-axis along with 0 from the complex plane, and now everything is fine. The principal logarithm is continuous there, and this equation is satisfied. So we have a branch of logarithm. Okay. So tomorrow I shall explain more on this topic. So I think I shall stop.
Sir, I have a question, sir. Hello?
Yeah, please.
Sir, we have seen the definition of the branch of a logarithm, but I want to know that how it has come, and actually how the condition e to the power fz equal to z has come. All of a sudden we have a definition. But I want to know the origin and the concept behind that, and why the branch of logarithm concept has appeared here.
To make this, you know, if you just look at the definition of logarithm, what is that? It is defined this way, right? It is a multivalued function. It is a multivalued function, but when you restrict the argument on an interval of length 2 pi, an interval which is half open, half closed, and of length 2 pi in the real line, then it is a single valued function. The question is whether that single valued well-defined function can behave well. If we have a single valued well-defined function, then we can talk about its continuity, its differentiability, and many other things. And we call it a branch. Now the question is, if we want to talk about continuity of that function, which is well-defined and single valued, then we have to make sure it is continuous everywhere first. Okay? But we are seeing that it is not continuous everywhere. Okay? This is the motivation. We want to make every single valued log z. If we want to make it single valued first, we have to restrict argument. We have to restrict the argument z in between an interval of length 2 pi, as I said always. Okay. For example, if we restrict it between the minus pi and pi, with the minus pi excluded and pi included, we have the principal argument, and consequently we have the principal logarithm. And if you have the principal logarithm, you just look at, it's a well-defined function. This is the principal logarithm. It is a well-defined function for all non-zero complex numbers. It is single valued and it is nice. Now the question is whether or not we can talk about its continuity or differentiability and rather analyticity. Those things will come into picture. The next speaker will describe all this, you know. We shall see that, you know, if you have a branch of logarithm, then it is analytic actually. You will see that it is differentiable everywhere in the domain. But if you want to make it continuous fast, the least thing that we can do is we just remove the negative x-axis, because this part of the definition, this argument part is not continuous there, but it is continuous elsewhere. Okay.
Okay, sir. So it is just because we want to make log z continuous.
You want to make?
Just to make the log z continuous, and then we want to
single valued. When it is single valued, mind it. Okay. We are talking about logarithm when it is single valued. Otherwise, it's of no use. If you have a multi-valued function, you cannot do anything with it. Once you have a single valued function, when you can make it single valued, then you can talk about its differentiability, its continuity, and all other properties that a function can have. Okay. So the least thing that we do is continuity. That is the first thing. That is the first step, whether the function is continuous. The answer is yes, the function is continuous, but not on the whole punctured plane. Not on the whole punctured plane. Where it is continuous? It is continuous on the entire plane except for the negative real axis. So let us remove the negative real axis and make it continuous. So that is the first step. So we make, we have made the first step. We have made that the function is continuous. We have made sure that the function is continuous. And next step is whether we'll see whether the function is differentiable or not. Okay, that will be the next step. If it is not differentiable for some points, we will remove them. Okay, if we find that it is not differentiable at some points, okay, then we will remove them. Let's see. But that will not happen. Just in advance, that's a good news. That will not happen. Anyway, so that is that.
Sound out, sir.
Hello?
So every continuous function have a branching logarithm.
Every continuous function
Have a branch of logarithm.
If it satisfies this equation, if it satisfies e to the fz equal to z.
This exists for every continuous function.
That is a question that I would like to ask the audience. Your question is whether anything beyond logarithm exists or not. That is the question, right?
Yes, sir.
Yes. So can anybody tell me the answer? So this is the general definition. What C is asking is the following: anything beyond the logarithm, any function other than the logarithm, can it satisfy e to the fz equal to z? The answer is already given. The answer is already given. If you just look at the first statement that I made today.
Then, sir, it would follow the definition of a logarithm.
So you just look at the first statement that was made today. The values of log z are precisely the complex numbers w such that e to the w equal to z. So what are the possibilities? What are the possible avenues? You know this. This is given in terms of numbers, right? But the notion is clear that the exponential function is the reverse of logarithm. Okay. Okay, I'll stop here today, and Professor Allu, tomorrow there will be a class at 5 o'clock, right?
Yeah, actually, thank you for